welcome back to next video. And actually here we will see the metal metric composites. Okay, in the last video we have seen polymer metric composites. So here in metal metric composites, actually it's a group of materials. Okay, like it can be either metal, it can be some alloys, or it can be some intermetallic compounds, as which we discussed earlier. So what happens is that, like, it is incorporated with some kind of reinforcing phases, which can also be some metals, like such as some particulates, viscous, or some continuous fibers. Okay, so these the peculiarity is that these materials like MMCs when can be well utilized at higher service temperatures than their base metal counterparts. So that this is the particularity of this kind of materials. So the reinforcement, when it's added to these metals or alloys or some compounds, so when reinforcement are added, this can improve the specific stiffness, specific strength, its abrasion resistance, the creep resistance. It can also increase the thermal conductivity and dimensional stability. Okay, in comparison to polymer metric composites, it poses like higher, it can be operated at higher operating temperatures, non-flammability is another property, so greater resistance to degradation from the organic fluids which can come, so and better wear resistance. But one of the disadvantages that in comparison to polymer metal composites, these metal metric composites are much expensive. So this table represents the properties of several metal metric composites. Okay, so here, like, the fiber phases are carbon, boron, silicon carbide, alumina, carbon, borosic. Like the metrics can be from aluminum, various aluminiums, magnesiums, and alloy, and tin, etc. Okay, some of the classes you can see the fiber content, density, longitudinal tensile modulus, and longitudinal tensile strength. Here, this table gives you an idea and gives a good settlement to your knowledge about these MMCs. So now the classifications of them. MMC are classified basically into three. The first one is layer composites, second is the fiber reinforced, third dispersion. So layer composite means in each layer composites are arranged well in each layers. Here next, in fiber reinforced, you know that its fibers are dispersed in a matrix of metal, and like the third one is dispersion and particle range. So the particle size are just mixed with the matrix. Now let us see the matrix materials. So metric materials, like we will, as discussed earlier, it can be super alloys, some alloys of aluminum, magnesium, titanium, copper. So reinforcements can be particulates, like fibers, both continuous as well as discontinuous, and it can be some viscous also, but we need to consider the cost effectiveness, so that viscous may be removed, but the fibers are much pointed or focused. So the continuous fiber materials, which that includes the carbon, silicon carbide, boron, alumina, and refractory. Discontinuous reinforcement consists primarily of like silicon carbide viscous. It can be chopped fibers of alumina and carbon, and particulates of silicon carbide. So these are some of the examples of. So this automobile makers, okay, they have introduced this engine component consists of aluminum alloy matrix. Nowadays, like if you see the engine, its casing and all, it's all made of this aluminum alloy, but inner portions, inner sleeve which covers the cylinder part, is mainly made of steel. That's to remove or to avoid the wear. but remaining parts all are made of this aluminum alloy matrix, which is like reinforced with alumina or some carbon fibers. The major aim is to have the lightweight. This lightweight increases or improves the what to say, the mileage, and the fuel improves the uh, fuel capacities. So this it, and second thing is that it provides very good wear resistance, and the thermal distortion is also very significant. So that's all for this metal metric composites, and in the next video we will see ceramic matrix composites. Okay, this one here this is ceramic metric composites, and please students, please note that in the notes which is given here, it is mentioned as mmc. Please correct the title. Okay, so ceramic metric composites, here the peculiarity is that the both the metrics as well as the fiber parts are both ceramic here. Okay, so why we use here, why we use these ceramic fibers in the ceramic matrix? So that's the doubt. So like we know the conventional ceramic issues, that is it will fracture easily under small mechanical or thermomechanical loads, because the cracks initiated by small defects or some scratches, it can propagate very easily. So like if we introduce some kind of fibers, like here what we are adding is nothing else but the same ceramic fibers itself. So this will increases the crack resistance and the fracture toughness. So with this where like toughness. So the monocrystalline viscous or platelets are the fiber part which we are embedded into the matrix. So how this will function? Let us see. So the basic properties of the any ceramic is its high strength and very high Young's modulus, but the fracture toughness is very less. But when we introduce the reinforcements into this matrix, what will happen is that its fracture toughness will be improved. Okay, so let us see. This is a crack. This is a crack which is in an ordinary ceramic. That is tetragonal zirconium dioxide particles. So what will happen is that this monoclinic zircon particles, like it will just resist the propagation of the crack. In this way, actually, this ceramic metric composites works. So some of the applications in the space, gas turbine, brake distance, slide bearings are here, and so these are the its properties which improves, so that these ceramic matrix composites are applied in these areas. So next is carbon composites. It is developed in 1950, and the composites are the family of this material where carbon or graphite, we can say graphite, is matrix is reinforced with again with carbon or graphite fibers. So this desirable properties like with high tensile modulus and high tensile strength up to this one 2000 degrees centigrade. That's a highlight, and again resistance to creep, relatively large fracture toughness values, all these things. So one of the disadvantages is that the high fabrication cost. So it is very much limited to the aerospace and the military application. So moving to the last section of the composites, that's hybrid composites. Hybrid composites, the name itself suggests that some combinations, some hybrid combinations are used. Like here, what we are using is that we are using two or more different kinds of fibers in just one single matrix. Okay, so what is that? What we benefit is that we will get all the better properties, individual properties, when it is combined. So these are the applications where it is used. So lightweight land, water, air transport, structural components, sports goods, lightweight orthopedic components, and all. One of the examples is that the carbon and glass fiber. So these are the two reinforcements which is added into like matrix polymeric resin. So what happens is that the carbon fibers are very strong. It is relatively very stiff and also possesses very low density reinforcement. But the disadvantage is that it is very highly expensive. But come to the glass fibers, see, it is very inexpensive. But it lacks the stiffness as that of the carbon fibers. So when they combine, what's the benefit is that we will get a strong and a tougher and high resist or high impact resistance. And one of the other highlight is that it can be even made at a lower cost than either of all the other components. So that's the benefit of this hybrid composites. So these are some of these research portions come from. So by this we just wind up the composite topics. It's very interesting and it's a very good area where a lot of students can do the research, and so some few of them can get jobs also. So with this I just wind up the thing. The next video we will see the dielectric components, polarizations and all those steps. Thank you for the attention.